So in this video, I'll discuss the solubility of ionic and covalent compounds. So before getting into solubility, I want to make sure that you recall the differences between ionic and covalent compounds. So recall ionic compounds are formed when oppositely charged ions become attracted to one another. You can see this form with the metal and the nonmetal, or you can also see polyatomic ions involved. The best way to think about it is that you have a positively charged cation paired with a negatively charged anion. These cations and anions can be monatomic or they can be polyatomic. And then covalent compounds occur when atoms are sharing electrons. So with ionic compounds, the electrons are transferred, but with covalent compounds, the electrons are shared. And you see these types of compounds when nonmetals share electrons with other nonmetals or metalloids. And so you want to make sure that you're able to look at a chemical formula and determine what type of compound you have. So for instance, if you were given the formula NO2, you want to look at what type of atoms are present. You have nitrogen, you have oxygen. They're both nonmetals. So that indicates that we're dealing with a covalent compound. I could have also looked at, for instance, I could have had sodium and oxygen. Sodium is a metal, oxygen is a nonmetal. So in this case, I have an ionic compound. I could have done the same thing with polyatomic ions. So for instance, I could have potassium, sulfate. I have a monatomic cation, polyatomic anion. Again, I have an ionic compound. So you want to be able to determine what type of compound before you're able to distinguish whether or not it's soluble or insoluble. And when we're talking about solubility, soluble just means that things will mix well. So these substances will combine to form a homogeneous mixture. Recall a homogeneous mixture indicates that we have two or more pure substances that are physically combined and they create a uniform composition. We also refer to this as a solution. If they're insoluble means that they do not come together. Now, when thinking about things being insoluble, that doesn't mean that zero amount of it dissolves. You may have a very small amount that dissolves, but so little of it dissolves that it appears that none of it has dissolved in that, whatever that solvent is. And so insoluble, we're not going to see a homogeneous mixture. We could think of that as a heterogeneous mixture. And so recall with the heterogeneous mixture, you have two or more pure substances that are physically combined, but there's no uniform composition. So examples of soluble and insoluble, you could think about salt water. When you add a small amount of salt in water, it looks like water, but the salt has dissolved. So you have something that is soluble or able to dissolve inside of water. Insoluble, we could think about oil and water. So if you've ever looked at oil and water, you notice that they don't mix. You can think about a bottle of salad dressing that contains oil and water. When it's sitting on the shelf, you see two distinct layers. Once you shake it up, then it appears to mix together. But oil and water on its own are insoluble. They do not mix well together. So this will help us when we're trying to predict solubility, thinking about the fact that these things have to come together. When it comes to ionic compounds, there are little tips and solubility rules that we can apply to determine whether or not that ionic compound is going to be soluble in water. When it comes to covalent compounds, we have to think about things a little differently. So let's focus on the ionic compounds first. Again, these are formed when cations and anions combine. So you have a solubility table that I am providing you. Now there are different versions of this table. Some will include more ions, some will include less ions, but regardless of what table you're looking at, this allows us to predict and determine the solubility of an ionic compound in water. And so this will allow us to determine whether or not an aqueous solution will form. Recall, aqueous solutions simply mean that something is dissolved in water. So in other words, it is soluble in water. The way that you read this table, you want to look at the ions that are present in that compound, and that will determine whether or not, based on these rules, whether or not it's going to be soluble or insoluble. So if we think about one of the examples that I showed previously, potassium sulfate. So remember that was K2SO4. So when looking at a solubility table, most of it is going to be based on anions, but you do have a couple of cations that are provided. So if you look at the very first row of ions, it tells you that group 1 metal cations along with ammonium, and it shows you what those formulas are. And the rule tells you that these are always soluble. So in the case of potassium sulfate, potassium is a group 1 metal. So based on that rule, we know that it's always going to be soluble. We could have also looked at the fact that sulfate is present. So sulfate is a little further down. And so if you look at this row, you'll see sulfate. And so sulfate compounds are generally soluble, and it tells you that they're soluble with ions, but you want to look at the exceptions. Always look at the exceptions. The exceptions mean that the opposite will take place. So sulfate compounds are generally soluble, but the exceptions include strontium, barium, silver 1, mercury 2, and lead 2. Any sulfate compound containing these ions are exceptions, meaning that they will no longer be soluble. Instead, they will be insoluble. But in our case, we have potassium sulfate, which is soluble. So because it is soluble, that means that it would dissolve in water to form an aqueous solution. So we can look at another example. So let's say we were dealing with, let's say, iron 2 hydroxide. So iron is not one of those group 1 cations. Those are the only cations plus ammonium that are listed. Everything else is an anion. So we have to focus on the anion that is present. In the case of iron 2 hydroxide, the anion, the negatively charged ion, is hydroxide. So when we locate hydroxide, it's at the very bottom of this chart. Hydroxide compounds are typically insoluble, but again, you want to look at the exceptions. The exceptions include calcium, strontium, barium, lithium, sodium, potassium, and ammonium. Iron is not one of those exceptions. So what that means is that this is going to be an insoluble compound, so it will not dissolve in water, so it will remain as a solid. And so we can look at this chart, look at what ions we have, and then look at whether or not that represents a soluble or an insoluble compound. Again, if the compound is generally soluble, which is what we see up top, these compounds containing those ions are generally soluble, so these. However, you always want to look at the exception. If it's generally soluble, but the exception has to be taken into account, that exception is going to be the opposite. So the exception is going to be insoluble. When you look at the very bottom of this chart, these compounds are generally insoluble. But again, you want to look at the exception. If any of the exceptions come into play, then it's going to be the opposite. So those exceptions are now going to be soluble. So when looking at ionic compounds, this solubility chart or table allows us to predict the solubility based on the ions that are present. If that ion is generally soluble, we'll know that, but we also will know that the exception to that would now be insoluble. If the compound with that ion is generally insoluble, then we know that, but we also know that the exceptions are now going to be soluble. So that's how we can determine solubility for ionic compounds. For covalent compounds, we have to think about the golden rule of solubility, which is like dissolves like. With covalent compounds, it goes back to intermolecular forces. Can these form attractions with one another? Do they have similar properties, such as polarity? If they do, then they are alike, and they will be soluble. So what this tells us is that if we have a nonpolar covalent compound, it will be soluble in things that are nonpolar. So for instance, CO2. Carbon dioxide is a nonpolar molecule. If you think back to the Lewis structure, so I'm not going to go through the rules for Lewis structures. I'm just going to draw the structure out. This is the Lewis structure for carbon dioxide. It has the linear geometry. It has two polar bonds. So you have a dipole pointing in the left, the exact same dipole pointing in the opposite direction, so they cancel each other out, making this a nonpolar molecule. So carbon dioxide would not be soluble in water. So it's not soluble in water. The reason why is because water is highly polar. Carbon dioxide is nonpolar. These two things are not alike. Nonpolar and polar are not alike. They have different properties. They have different types of attractions. Nonpolar will only participate in London forces, or those dispersion forces. Polar can also participate in dipole-dipole, and depending on the molecule, it may possibly also participate in hydrogen bonding. So in the case of water, it will participate in hydrogen bonding. So you have something that's looking to form those strong hydrogen bonds, but then you have carbon dioxide, which cannot form those bonds. So these are two things that are not alike, so they will not be soluble. If we had a molecule such as NCl3, again, I'm not going to go through and do the Lewis structure step by step. But if you had to go through that Lewis structure, this would be the structure. So even though you have these nitrogen-chlorine bonds, which are polar, so you have dipoles going in all three directions, this is still considered to be a polar molecule. This is a polar molecule because the electrons are not spread out throughout the entire molecule in equal directions and equal strengths in all directions, is what I should say. Let me rephrase that. The dipole or the electrons are not spread throughout this entire molecule equal strengths in all directions. You have the electrons being pulled in three directions, but then you also have these non-bonding electrons that belong only to the nitrogen. So therefore, this is a polar molecule. Because this is polar, it's going to look to be dissolved in something that is polar. And so this one would be soluble in water. Because water is polar, this nitrogen trichloride is polar. So it is soluble in water. How soluble may vary. Things that can participate in hydrogen bonding, of course, are even more like water. So those substances may be able to dissolve even more of it in water than this. However, this would be considered to be soluble in water. So when you're looking at covalent compounds, you want to look at what type of compound. If it's nonpolar, it's going to be soluble in things that are nonpolar. If it's polar, it's going to be soluble in things that are polar. If it's nonpolar, it will not be soluble in things that are polar. If it's ionic, so if we have ions present, recall your different types of intermolecular forces. You had London forces, which were the weakest. You had dipole-dipole attraction forces, which occur between polar molecules. You had hydrogen bonding, and then those apply to all covalent compounds. But then you also had something that was even stronger, which was the ion dipole attraction force. That occurred when an ion was in the presence of something polar. So those attraction forces also help you with predicting the solubility. So if you have an ion present, it will be soluble in things that are polar. So if we had a single ion present, so for instance, if we had, let's say we had the sodium cation, if we have this in the presence of water, they will be soluble. Somebody say is soluble. Because they can form those ion dipole forces. So if attractions can occur, if these substances are similar or like in terms of properties and polarities and intermolecular forces, then they will be soluble. So this is how you can determine the solubility for different compounds. Again, with your ionic compounds, you want to look at that chart. If you don't have a chart, you can also look to see whether or not it tells you an ionic compound is soluble. So for instance, if you're just told sodium chloride and you're told AQ, anytime you see this AQ, that means that whatever that substance is, or in this case that sodium chloride, is dissolved in water. In order for it to be dissolved in water, that means that it's soluble in water. If you didn't see that, so if we saw something, for instance, like MgSO4 solid, and we know that this is added to water and it's still a solid, then that means that it's insoluble in water. And so again, we can look at the chart, or we can just look at the physical states that are provided in order to predict and determine the solubility for ionic compounds. For covalent compounds, we have to think about what type of compound it represents in terms of polarity. So is it polar or is it nonpolar? And that will then dictate how it will be soluble in other compounds or other solvents. If it is polar, it's going to be soluble in other polar substances. If it's nonpolar, it's going to be soluble in other nonpolar substances. So I hope this helps. If you have any questions, please let me know. Thank you.